As you see, the title of my talk is about material science and mechanical. And I will, first of all, motivate why I give this talk and give some introduction and talk about physics-based property models and give some example for low alloy steel and a little bit more about our work for alloy 718. And then, of course, give some final remarks, so a typical outline of a talk. So the motivation is basically what I have to do myself. I have to learn a lot of material science. I'm mechanics in the beginning and started my PT in welding, and I had to learn words like phase changes, etc. So my main motivation is that most models need to know more about material science models, because we have a lot to pick up that is available for us to implement in software and in order to improve our models. And even if we are not working on the kind of details models like I am and other working where we really want to simulate the microstructure, even for simplified models, you better know what's going on in order to know what you can ignore and the effect of what you neglect. So even working with simplified models requires some fundamental understanding of the material behavior during these kind of processes. So I'm just now working to complete a book about this. So I will give you some glimpses from that one. So we have some basic simulation approaches. And we work on the red line here, more complete history models where we simulate the microstructure and properties. But they are quite cumbersome. They, of course, enable that you can, even if you have, when you have more physics design models, you can even go around with the chemistry and design material and manufacturing process in order to get a specific performance. So it gives a lot of possibilities, but it takes computational time and you need a lot of input. You can, of course, do then more simplified analysis where you can, particularly for powder bed processes, where you have a large number of layers, you will want to reduce some of the history of the material behavior. And typical inherent strain approach, I think Albert too will talk about that later this afternoon. So you can climb up to more simplified approaches. And of course, you can go down to more detailed models like Caroline talked about earlier today. So with this is the motivation for my talk, that we all need to know more about material science and what we can pick up from that box and use in computational thermomechanics. This is a case manufacturing chain we're looking at, but it could be an AM process. In fact, this metal deposition step is AM. And then there's some machining on the surface, which is the post process also used added to manufacturing products. And you can have heat treatment and you can have hot isostatic pressing. So when you do this, you subject the material to quite varying stress, strain, and temperature, as well as time scales, which normally we use different models depending on where in this window we are. And we have to switch models if you move out of it. So in the beginning, when I worked with welding, I use an rate independent plasticity model, temperature dependent for the welding, and then for the heat treatment, I had to go over to the viscoplastic or creep model, which makes a problem because you lose some history between, because these models are not calibrated with respect to each other. So we want to have a model, at least in our work, that can cover this window. And therefore we go to physics-based models coupled to the microstructure evolution. Physics-based means that we can look at, you can say, for example, strain hardening. Effective plastic strain is not the physical parameter. You cannot observe it, but you can observe dislocation. So we use dislocation density as a measure of the hardening, for example. So that kind of models is what we say, I would like to call is the way of merging material science and mechanics in modeling. Modeling is the meeting place for these two fields. A physics-based model, in my definition, is not an ab initio model. It's not, you still have calibration parameter because you simplify the what's going on the micro level, but now you have, as we heard, a lot of variety and the microstructure varies. So we need some kind of average behavior on plasticity level. So we still end up with some kind of calibration parameter. But of course, if the models are well formulated, we know the range of these parameters quite well. So properties and models of properties, I mean, they depend on the different scales and vary with the particular temperature in this case. And one should be aware that transport properties are more sensitive to the microstructure features than storage. So, for example, heat conduction is more affected by chemical composition than heat storage, heat capacity. Plasticity is more sensitive than the elastic modulus. So they are more or less demanding if you want to have a model that connects more to the physics. When you look at the characteristics, we have some typical variables. You will see some equation, but I will just give you, you can say the impression, I won't teach you about it, but like the lattice parameters, which is important not only for the thermal expansion of material, and that can depend on the alloying also. It also affects the dB frequency or the corresponding dB temperature, giving a temperature-dependent dB temperature. As I said, it's not really a temperature, it's the frequency of the lattice. The Curie temperature is one parameter that comes in, particularly in the steels. And it's also like composition dependent. And we use them to scale the temperature in our model. So we divide temperature by either dB temperature or Curie temperature. We combine that for low steels with a phase change model, quite simple one, but still quite flexible. And in fact, if we know nothing more than chemical composition, we can bring it in and predict based on statistics, the different transition temperature, CCT diagram, TTT diagram, transient histories. Of course, if we know more about martensite start and bayonet start, etc., we can improve the predictions. So one can go on and make a better prediction. So have an example of, I think it was a 3420 steel measured and predicted TTT diagram. Isothermal heating diagram, not equal good prediction, but we have a possibility in this model to have the effect of heating rate on the austenization start and finish temperatures. They go up with the heating rate. So that kind of features. So we can then, for example, start with a given equilibrium composition of material. We heat it up and we compute the phase changes. So during heating, in the end, everything is austenite. We cool it down. And if you cool it quickly enough, the austenite disappear and we have martensite. And based on the lattice parameter, we compute the thermal expansion. One example. This is an example of heat capacity. The dB model, where you have the phonon contribution, electron contribution, and the magnetic contribution. In fact, these have no calibration parameter. This one has a theoretical value, but it's a little bit calibrated. This has some calibration parameter. But it's for the alpha phase, measurement of symbols. For the austenite phase, symbols and measurement. So we can fairly well tell for, in this case, it's iron, how the chemical, not the chemical composition in this case, but how the phase changes affect the effective combined properties of the FCC and BCC lattices and how they vary with temperature. Electrical conductivity, where one assumes that the electrical resistance is the sum of imperfections and phonon and electron interaction and also magnetic part. Symbols of measurement and the lines are the model prediction. It has some calibration parameters. That one is also used to compute the heat conductivity due to the electron part related to the electric resistance, and then you add in the phonon part. And the phonon part is quite important for steels. Normally we say the electron part is the most important for metals and alloys, but the phonon part is quite essential part for steel and iron. Elastic properties, calibration curve, where we can predict the FCC and BCC phase for the bulk models and shear modulus. And then we can from them that calibrate the model compute the Poisson's ratio variation with temperature, and we include some measurement here. This is of course quite uncertain. It's not so easy to measure. And then we have a model for shear model. For us, the shear model is extremely important because that goes into the plasticity model. So if we change the shear models of a material, we think, oh, that was a wrong number. We have to recalibrate the flow stress model. So we want a good model for the shear models. Just for information, this curving down, they usually vary quite linear when you're above room temperature. But there's a small curvature here. That's because we scale with temperature divided by the debut temperature that vary with temperature. This part is the BCC, is the magnetic transition. So this part is scaled with the Curie temperature, how you go from over to the non-magnetic part. Okay, that was some glimpses of physics-based property models for steels, or low alloy steels rather. Alloy 718, this is old result where we calibrated dislocation density flow stress model together with the precipitate model. So we had the model for precipitate growth and how that affected the material behavior during aging. So we had to do some tests for different aged material to calibrate the precipitate contribution. So that was done already, but we're working on extend it, and I will give some forward look for the future. The original one had some effect of the strain hardening, or interaction between near parallel dislocation, and where we trace the immobile dislocation density. A glide part where they interact with near orthogonal dislocation, which has a given format of this type with some calibration parameter and some effect of dynamic strain aging. And then it also included precipitate hardening due to bowing around larger obstacles and cutting through smaller ones. So that was the basic of the previous result. What we're working with now is to include the Hall patch term, high strain rate defect for machining cases where we have electron and phonon drag on the dislocation, solute hardening, dynamic strain aging, which was this term, which we hadn't used before, and also discontinuous recrystallization. So I will end up giving some example of that before I conclude my talk. So we have extended the flow stress as contribution of these different material resistance against dislocation motion, which makes up the yield stress. This is a long range part, which you always have to overcome to get plasticity. This part is what, when you're above the yield limit, you get a certain strain rate, and they give additional resistance depending on the temperature and the strain rate. We find results from measurement of the effect of chrome in pure nickel, and that's the symbols here. We use the typical available model where you have modulus misfit between the host lattice, nickel, and the chromium, and also size misfit. And you can combine them according to models into an effective shear contribution to shear resistance in the material, which is proportional to the solute concentration raised to 2/3. And then you can translate it into an effective contribution to the flow stress. And the models is the lines. And of course, it's not a perfect match. It's not that easy. Luckily enough, we haven't weighted, but the interesting range for alloy 718, it's fairly okay represented. Low concentration chromium is not well, high seems to go away also. So we can then predict, and we use the same model, but we have different, basically same down here, but we have different models misfit and size misfit. So we could include more solutes from the 718 and compute how the additional strengthening depends on temperature and plastic strain rate, for example. Dynamic strain aging is where dislocations moving and solutes hang on to them, they diffuse into them. And it's the rate dependence effect where we use a steady state concentration solution based by Cottrell. So it's what we call Cottrell cloud, where we can compute how much extra solutes we have near the dislocation. If they're too large for the lattice, they stand on the tensile side of the edge dislocation. If they're too small, they stand on the compressive side. But you get some increase, which will give an additional factor of magnifying the glide resistance in a model. And it looks like here, the contribution to dynamic strain aging factor. So this is the factor that is multiplying another term. So it shouldn't be MPa here. And you can see then that in certain temperature region, the dislocation start to get dragged by the solutes that are diffusing fast enough to hang on. But if you increase this strain rate, they cannot hang on anymore, so it goes down the contribution. The typical cause of dynamic strain aging, where you, even if you here increase the temperature, you suddenly get an increase in the flow stress, a typically observed acceleration on the stress strain curve. Dynamic or discontinuous recrystallization. Usually we say dynamic discontinuous RX, DDRX. I don't like the word dynamic. In this model, I won't go through it, but basically we have a body driven by dislocation density. When it's high enough, we trigger this. And then the dislocation goes down because you grow new grain, which has a lower dislocation density. So we change the so-called strain hardening term. We also change the Hull patch term. And we can look here when we look at a different plastic strain, and we have some example of different strain rates. This is not alloy 718 parameter, but if you have a low strain rate, for example, this one, 0.01, you trigger the recrystallization, the flow stress goes down. And then if you wait after the deformation, nothing happens because you have reached the value you can reach for that kind of deformation. If you do it very fast, you see very little. And if you look at the model also, you see very little recrystallization, small recrystallization fraction. But if you stop and wait, it goes down, the flow stress, because you trigger the new nuclei for the grain, but they need some time to grow because there's a limited growth rate due to the motion of the dislocation, or the grain boundary. So therefore, it includes dynamic as well as metadynamic strain recrystallization. So I prefer just to call this continuous RX. And now I think I'm in time to conclude. So I have always had a question when I work with welding and computation welding mechanics. We've never been able to solve the problem of defect prediction. So if you have a small sample and you test it, weld a small piece and test it, you have the correct microstructure and defect structure, but not the stress state. So typical for critical application, you end up with full scale testing when you have a welded structure that is important to check out the lifetime. So I am more positive now because you can say welding, when you were able to model welding, it was not that hot subject. So it was not, we can say, sexy subject. Not much money went into it, and it's a limited community working on it. Now it's much more money and research and all over the field. So I'm maybe more positive now that we can go forward also more in defect prediction or estimates, at least in the AM. I will also say that, as I mentioned in introduction, that we cannot really do very large component with powder bed fusion because too many layers. Even for the application, we might have problems. So of course, they need to be combined with some faster method where you can look at the whole components. So I think there is at least an interest that you can use this kind of more detailed model to develop the material description for inherent strain models, because typically you look at the wall and you do a test. And you don't care whether it's a bottom or top layer, but they experience different temperature history and have different properties. You might need to tailor that. I want this kind of behavior in my inherent strain model in this region. And then you could maybe use this kind of more detailed model as kind of virtual test, where you look at the small part of the structure in order to know how to treat that region in a simplified model on the larger scale. So with that, I'm done. Thank you very much for your attention.
Thanks a lot for your very interesting talk. So the talk is open for questions. Are there questions from the audience? Yes, maybe there is one here. Okay, please, Caroline, can you proceed with the question?
Lars-Erik, thank you very much for this really nice talk. I have two different questions. The first question is, how are you modeling the elastic properties, the elastic modulus or the shear modulus near the melting point? This is the first question. The second question is, during additive manufacturing, we have solidification far away from equilibrium. So you have strong non-equilibrium solidification microstructures. In your equations, which you have shown, I don't see really where this kind of non-equilibrium structures go inside your modeling effort. So do you have an idea how this in situ microstructures can be modeled?
The short answer, of course, is that we don't model them. Basically, when you look at the fluid behavior or very near the molten region, we have basically left it out. I mean, typically, computational welding mechanics context, I used to say that we treat the weld pool as a chewing gum. It's just a soft solid. So we cancel out all previous hardening when it melts. And then you can say our model take place when you come down in temperature somewhat below the T solidus. So that's the answer on your first question about how we treat that one. Regarding non-equilibrium, some of these models do include non-equilibrium. Of course, the phase change model is based on that one. The one for the steel is more ad hoc, but the one for the precipitates growth, of course, is a non-equilibrium one, where you have a driver to minimize Gibbs energy that gives the growth of the precipitate. So it's a little bit varying, but we have nothing about the solidification in these models. In welding, people have tried to combine the small scale, looking at the weld pool region, but they find it extremely cumbersome. So typically, we cut the border and say, well, now I look at the weld pool behavior, and people do detailed models of that, and they don't look at the whole structure. So
I'm asking because you showed this example for Inconel 718, and for this it's well known that during additive we find phases which we wouldn't expect for normal processing due to the strong segregation effect. So we have different phases, and this is the reason why I've asked this question.
Yeah. the precipitate model is of course too limited to handle that kind of details. It's just focus on the niobium diffusion and creating of double gamma prime. We don't look at the gamma prime either. So it doesn't know anything about these details.
Okay, thanks a
And
lot.
we have, I just can mention that we do have a post-process model for hot cracking, where we look at the molten region between the grains, which is the hot cracking source. And there we look at some segregation in order to predict when it starts to solidify, but that's a pure post-process.
Thank you very much.
Thank you. We also have a written question from the audience by Juan Famin Wanali. So the question is, can we assume no DSA at room temperature or at low temperature with very low strain? And can we estimate the residual stress based on strain? This is
the first part, of course, is that we don't expect it at room temperature. I mean, it requires some diffusivity on the solutes. And of course, you can say that maybe hydrogen diffuse faster, but I think even for that, it won't matter for room temperature. So that is not an effect. And then you say, can we estimate the residual stress based on strain? Well, what you measure is residual, or you can say the elastic stress. So when people measure residual stresses, they measure elastic strains, and then we do some assumption to compute a residual stress. So that's possible to do. And the problem, of course, is the measurement resolution and what kind of techniques you're using. As you have you would like to have a small homogeneous region, so you don't need so much beam time, for example, if you use that method. But in principle, you can do that. You can have the hole drilling techniques. You measure an elastic unloading and have some model assumption to say what the stresses were.